Alright, silly people, here's the situation. We have a system that is comprised of n states that can have energy 0 or delta, um, and you have to show that the number of ways that omega of e, so show that the number of ways omega of e of arranging the total system to have an energy equal to r times delta, where r is an integer, is given by this equation here. Um, Omega of e is equal to n factorial over r factorial times n minus r factorial. Um, so this part of the problem is more of a conceptual check, really. Um, Whenever you're looking at a system like this, where you have, say, a number of particles numbered 1, 0, 1, 2, 3, and so on, that can be in a state 0 or another number like delta or 0, only two different states, um, then really what you're just doing is you're seeing n choose r for the amount of different arrangements where the number of deltas is equal to r, right? So n choose r is verbatim n factorial over r factorial times n minus r factorial. So that is the amount of um, permutations, arrangements, I guess, of the total system to have energy equal to r delta. Next part of the problem says we're going to remove a small amount of energy s delta from the system, where s is much less than r, and show that it has some certain form. Um, so we're subtracting some amount of energy that they label epsilon from it. So now we're going to be choosing, it's n choose r minus s. We're removing amount of energy from the system equal to delta s. So it makes sense to just do n r minus s for the choose. And so it's n factorial over r minus s factorial n minus r plus s factorial. All right. Um, you know what? At this point, it's worth pointing out what omega of e is, um, using the Stirling approximation. Uh, that being that the natural log of some number n factorial is nln n times the natural log of n minus n, right? That's an approximation. So just looking at the natural log of omega of e, so that we're looking at the natural log of n factorial over r factorial n minus r factorial, which you can split up into multiple components, which I'm going to do. So it's natural log of n factorial minus natural log of r factorial minus natural log of n minus r factorial. Then apply Stirling approximation to each one individually. So n natural log of n minus n minus r natural log of r. This is an approximation. Plus r minus n minus r natural log of n minus r, and it's plus n minus r. Noticeably, this n cancels out this n, this r cancels out this r, and you're just left with the natural log terms, which we're going to then recombine whenever we raise the whole thing back to e minus n minus r natural log n minus r. Right. So then raising e to the power of this stuff on both sides of the equation, you get n to the n, you get r to the minus r, and you get n minus r to the negative n minus r. And then I'm just going to put that in a fraction. N to the n over r to the n times n minus r to the n minus r. That's a nicer way of putting the arrangement number. So now looking back at the energy displacement term, taking the natural log of both sides is going to be very similarly natural log of n factorial over r minus s factorial times m minus r plus s factorial. Right. Okay. So again, we're going to split this up and do Stirling approximation on each one individually. So it's going to be natural log of n factorial minus natural log, minus natural log of r minus s factorial minus natural log of n minus r plus s factorial. Under Stirling approximation is n natural log n minus r minus s natural log r minus s plus r minus s minus the n minus r plus s natural log n minus r plus s plus n minus r plus s. Cool. Again, the letter terms by themselves will cancel out. So negative n cancels out positive n, positive r cancels out negative r, negative s cancels out positive s, and you're just left with the natural log terms. I'm going to collect them like this, n ln n minus n minus r plus s natural log n minus r plus s minus r minus s natural log r minus s. Right. Now, raising e to the power of this junk, again on both sides of the equation, we're going to have n to the n, and it's going to be n minus r plus s to the minus n minus r plus s times r minus s to the minus r minus s. And then I'm going to put that in a fraction. It's going to look like n to the n divided by n minus r plus s, n minus r plus s, r minus s to the r minus s. All right. Now we're going to use the fact that s is defined to be much less than r only in the terms within the parentheses, so that r minus s will become just r, and n minus r plus s will just become n minus r. Applying that approximation to our stuff, n to the n over n minus r to the n minus r plus s. So r minus s to the r, oh, whoops. It's just r to the r minus s. And then we can factor out all of the stuff that we've seen before. So this stuff, and then leave behind r to the s divided by n minus r to the s. Okay. The first term is exactly equivalent to what we got before for omega e, and we're left with just the n minus r s. That is the new amount of arrangements after the change in energy. The problem also asks us to find the temperature of the system, assuming a Boltzmann distribution. So the way to do that is to use this equation, which relates the Boltzmann constant and temperature equal to the change in the natural log of the number of arrangements divided by the change in energy. So the change in natural logs then is just going to be the natural log of the initial state. So ln of omega e, and then minus the natural log of the new amount of arrangements, ln omega e minus epsilon. And then on the bottom, the change in energy is just, so we had an E equal to delta R, and then the other energy was delta R minus delta S. The denominator is really easy to evaluate. That just ends up being it's 1 over S delta. And then the top is natural log omega of E minus natural log, and then this was equal to omega E times R to the S over n minus R to the S. Okay. We can add these natural logs together so that they will be a natural log of its omega of E on top, as well as a n minus R to the S on top, divided by omega E times R to the S. The omega E's will cancel out. And we can factor the S out of the natural log because they both have the same power. So it's S times natural log of n minus R over R. And then the S's will cancel out. And you're left with the expression that Blundell wanted. 1 over delta natural log of n minus R over R. Pretty awesome. I forgot to mention this part. If you solve for if you solve for kBT, so Boltzmann constant times the temperature of the system, which I've written as y on that Desmos page, and then just I plugged in some values for n and r. If you plot the temperature times the Boltzmann constant from r equals 0 to r equals n, then you get that weird asymptotic form of the temperature, which just means that the temperature is starting quite low whenever R is really low, and then increasing exponentially, like when it gets to R is equal to N.